Okay, first I'd like to thank the organizers. Actually, my name is Seung from UNIST, and today I'm going to talk about the calculation of Exciton couplings based on the semi-empirical method with kind of spin-restricted ensemble-referenced Kohn-Sham approach. So actually, today I'm going to talk about two parts. First one is about the combination of the FTB and the SSR, the Rex method, with 2 electrons and 2 orbitals. And then I'm going to move to the 4 electrons and 4 orbitals to calculate the Exciton couplings. And before my main talk, actually, I would like to introduce the map of South Korea. And actually, sorry, here. All right. So actually here we are in Jeju Island, right? And actually we have several speakers from the main end of the South Korea. Actually, we have the Professor Eun Shin, the speaker in the yesterday from Yonsei University in Seoul, and we will have Professor Kim and from the Gyeonghee University, and now we have Professor Jae-woo Park from the Chungbuk National University, and Professor Youngmin Lee and Professor Hyungjun Kim from KST in Daejeon. And actually, Professor Choro Choi's group is in Daegu, the Gyeongbuk National University. And also we have speaker from Postec, and actually I'm here. So Ulsan, which is my institute is named as the UNIST, Ulsan National Institute of Science and Technology, and it's quite young institute. Actually, it was founded around 10 years ago, so it's quite young. So actually, yeah, here. So this is the map, the picture of our institute. Actually, it is surrounded by mountains as a kind of green area. Okay, so the air is quite good. No air pollution here, actually. So by the way, so we have some speakers from a kind of diagonal area of the South Korea. So actually, if you want to travel, okay, South Korea, then actually you can ask the speakers for inviting you, right? And you can actually enjoy the local food here, okay? So anyway, so I would like to also introduce my group, what's going on in my group. So actually, main work of my group is actually the kind of develop some coupled electron nuclear dynamics for the excited state phenomena. Actually, we were trying to develop some algorithm beyond the conventional surface of algorithm, so to take into account kind of the correct coherence and decoherence phenomena. So actually we developed a surface hopping based on the exact factorization to calculate the electron nuclear correlation correctly. And actually we developed a kind of open source code, which is called PyUnixMD. So it is actually Python-based program for the universal excited state molecular dynamics. So it is actually open, so you can actually access the code from this link. Okay, and we have several papers about this PyUnixMD program. So actually, I already gave a talk about this dynamics part in the previous the NHISS conference of 2012 and 2021. So if you're interested, you can actually watch the seminar recording, right? So if you're interested, then please watch it again. And then we have several occasions of these photochemical reactions, like this one. And then actually the third part is the development of the efficient electron structure calculations. So actually, whenever I perform this excited state molecular dynamics, the crucial thing is to have some efficient code to calculate these excited electron structure calculations. So we have actually 3 categories in our research group. So one is for the machine learning. So we actually try to build the machine learning potential surface from the machine learning. And another one is to develop some more efficient, but not as accurate as the ab initio calculation. So we actually try to use some semi-empirical approach to calculate the electronic structure for the excited state. Then the last one is about the orbital-based propagation of the electron density or coefficient, so which is suitable for the kind of solid state, so extended systems. So today, actually, I'm going to talk about this part, the combination of the semi-empirical methods with this ensemble density functional theory. So basically, what I will try to do is to calculate these kind of big systems. So this is the LH2 complex, right? And this one, actually, this picture comes from the Todd Martinez group several years ago. Actually, his group actually provides some methodology to simulate this kind of big, huge exon coupling systems, right? And actually, to simulate this kind of thing, actually, we should construct some exon Hamiltonians like this way, and actually, we can calculate kind of local extonic state with the ab initio method, and then we can actually construct some coupling matrix element with several approximations like this way. So, well, of course, this simulation doesn't include the protein environment, but still, it actually provides us some algorithmic approach to simulate these entire systems. So actually, my target is like this one. So we need actually some efficient calculation methods to simulate and to actually calculate kind of extonic stage and so on, each couplings. So what I want to do, what we want to develop actually is to eventually decouple the electron nuclear dynamics with the entire or partially, the partial system of interest. And to do that, actually, we need some efficient methods to calculate the exon coupling constants for the atomic simulation. And actually, previously in my work, dense functional tight binding based spin restricted ensemble Kohn-Sham, the REX approach with 2 electrons and 2 active orbitals was developed. And with this method, actually, we can calculate the local excitation energies and conical section structures. So then actually we can extend this approach for the larger active orbital spaces and active electrons, such as 4,4. Then you can actually describe the interaction among the ground state and locally excited states and charge transfer states. So this is the story of actually my talk today. So first, actually, I'd like to give a brief summary of the previous 2,2 approach. Actually, when I got a position in Korea, and actually Michael was in the same institute, and he was a visiting scholar under the Professor Kwang-Soo Kim's group. And actually, he gave a seminar about his approach, the SSR 2,2 approach. And I was so impressed, but because this method actually can deal with the kind of calculating conical section structures and as well as the correct potential surfaces between the S0 and S1 states. So I want to use the kind of methodologies, and I want to develop more efficient method based on the semi-empirical approach. So the idea is like this one. So for example, if we have active space with the 2 electrons and 2 orbitals, then we can actually imagine the total 6 microstates with the spin indexes like this way. Then, and also this actually methodology, I should say that this methodology was to develop to consider kind of highly correlated electron systems. So for example, the 2 Kohn-Sham orbital energies are nearly degenerate. So we should deal with kind of fractional occupation numbers and so on. So from this microstate, actually we can construct kind of several electronic states. For example, the perfectly spin paired state or the open shell singlet state based on the generalized valence bond theory, then we can calculate these kind of energies with a linear combination of the microstate energy, like this way and this way. Then actually we can make some we can also implement some state average scheme. So we want to minimize the overall these energies, then we can obtain the Kohn-Sham orbitals, which is suitable to describe these 2 states. And then we can introduce the state interaction like this one. Then actually finally we can calculate the adiabatic energies for S0 energy and S1 energy. So within these methodologies, actually we can deal with a bit of dynamic electron correlation. So we can actually describe the conical section very well. And also we can evaluate the analytic gradient. Therefore, we can actually search the minimum energy conical section structures, and also we can perform the excited state molecular dynamics simulations. So in our group, actually, what we want to do is to try to calculate the microstate energies based on not accurate semi-empirical approach, right? So this is the kind of energy expression in terms of the density functional tight binding approach. So we have several terms, right? We have several terms, and we have the zero solar energies and charge-charge interactions come from the charge fluctuations and spin interactions. And we introduced the long-range part, range-separated part, and also we have electron repulsion. The one good thing of the FTB approach is that we don't need to evaluate the integrals, right? So everything is parameterized. So for example, this reference Hamiltonian matrix element, or this overlap matrix element, or this electron interaction terms and spin-spin interaction terms, and so on. Everything is parameterized and tabulated in terms of the distance between the two centers, two atomic centers. So we don't need to evaluate the integrals at all. And so it's super fast, of course. But as you know, right, the drawback of this approach is the accuracy. So whenever I do some calculation with this tight binding approach, then actually the referee always says, do ab initio calculations, please. Even with I have the 1,000 atoms in the unit cell. But well, actually we did it and the paper was submitted, but that's okay. But anyway, so this is the energy expression of density functional tight binding. And this one is the self-consistent loop of the how to obtain the Kohn-Sham orbitals, because the Kohn-Sham orbital is not the eigenstate of the each microstate. So we have several kind of weird Kohn-Sham equations like this one. So this is not kind of diagonalization, simple diagonalization. Instead, we have pseudo-Fogg equations. Then if you solve this one, then you can actually evaluate the Kohn-Sham, we can obtain the Kohn-Sham orbitals, and we can optimize the fractional occupation numbers to minimize the previous the state average energies. So within this procedure, we can calculate the S0 state, the energies, and S1 state energies. So as an applications, actually, we try to find the conical intersection structures for several molecules, small molecules compared to our semi-empirical approach, right? But anyway, so this one is the red one is the reference structures, which is obtained from the first principle Rex approach. And then the colored one is the result from our methodology, the FTB approach. So the result is quite okay, looks okay. So we can describe some pyramidalization. Also, we can calculate, and we can construct quite nice structures. And also we can calculate this kind of G vectors and G vectors to which are related to the non-adiabatic coupling vectors. So direction is also fine, and magnitude is also fine. So here actually but I wasn't that happy, because actually this one to construct the conical structures, we should implement another parameters to obtain correct geometries. Here we have this kind of S, so we should introduce some scaling factors, which is not good. So, and then we try to try to develop more generalized, which is or more accurate method compared to the previous one. So what's the missing part for the previous methodologies? So actually in DFTB, the conventional DFTB formalism was developed under the Mulliken approximation. So in these Mulliken approximations, actually to evaluate these multi-center integrals, the atomic orbitals, the product of atomic orbitals approximated as this one here. So it's really, really simple one. Then after this Mulliken approximation, the integral evaluation, these two-center integrals are just simply this one here. So we only have kind of a, sorry, if you look at the index, we have just mu over there, alpha or beta. So we just have simple these two both terms of integral alpha, beta, alpha, beta, alpha. So we just have these terms. However, we don't have alpha, beta, something like that, which is actually essential for the accurate simulation. However, if we actually introduce kind of on-site correction term, then we can actually evaluate this product as this one. Then we can have this kind of this kind of term here. Develop more generalized approach for the dense functional tight binding calculation here. So we actually try to add these on-site calculations. Then we have if you look at these energy terms, we have mu nu and mu nu, something like that here. So we introduce these terms. Then what we can obtain is this one actually. We actually also evaluated conical section structures. Then if you have purely LC-DFT with the long-range correction part or orbital correction, on-site correction part here, then it's not good at all, actually. For some case, it's okay, but some case, it's not that okay. For example, this one and this one, right? We have large deviations here and here. However, if we introduce long-range and on-site correction simultaneously, then actually we can have quite nice conical section structure. This is just quite good. So we can actually now have the gradient for all configuration space. So we don't have any additional parameters. So this is ready for the dynamic simulation actually. And here actually we try to do some calculations with this Beringer motor system. In this Beringer motor system, we have a conical intersection structure with pyramidalization. As you can see here, the rotation of the blades is actually related to the conic pyramidalization of the ring, actually, the CC bond, central CC bond. However, if we just simply doesn't include the orbital correction not enough, then actually what we obtain is that the conic section is just the simple bond length alternation. So it's simple stretching of the central CC bond actually can give some access to the conical section, which is not accurate. Okay, the real structure is actually related to the pyramidalization of the central CC bond here. So if we just consider just partial orbital on-site correction here, then as you can imagine, right, we can have more access to the conical sections. We have fast decay of the S1 population, like this blue curve. However, the reality, we should have this kind of slower the decay of the population. So this is the true result. Okay. Then I would like to mention some computation time. So actually in DFT calculation, we just need just one core, CPU core. Then to calculate this system, we just less than 1 minute, a few tens of seconds. However, if you calculate this SSR method, first principle SSR method, which is implemented in TerraCam software, then we need kind of more than 30 minutes with the heavy GPU machine. So we have, of course, we lose some accuracy, but we have large enhancement of the computational efficiency. Yeah. So this is the summary of the 2.2. So what about the 4.4? So of course, thanks to Michael, okay, it was already there. So we already have several equations and how to evaluate the Hamiltonian matrix element, how to solve the Kohn-Sham orbitals. Everything is actually written in this paper. So what we just try to do is to implement this dense functional tight binding framework to evaluate these microstate energies. So here, actually, with these 4 electrons and 4 orbitals, we have actually total 36 microstates here. Then from these 36 microstates, actually, we can construct 9 electronic configurations based on this generalized valence bond theory. So we actually make some pair between orbitals A and D and B and C. So if we considering the kind of double excitation and this opposite singular interactions and so on, then we can actually construct electronic wave functions, and we can evaluate the energies and Hamiltonian matrix element. So here actually we have perfect spin pair system and opposite singlet, 1, 2, 3, 4, and doubly opposite singlet and doubly spin polarized straight like this way, and doubly excited states like this one. So we have total 9 states that we can evaluate the energies and coupling between those. So we are now moved to the excitons. So if we actually have some orbital pairs localized on the kind of respective monomers, let's say M and N, okay? So we have A and D localized orbital for monomer M. We have B and C localized orbital for monomer N. Then if you consider the coupling, the excitations, then this opposite singlet OSS1 state is related to local excitation on monomer N. And OSS2 is related to local excitation of monomer M. And OSS3 is charge transfer excitation. And OSS4, we have charge transfer excitation from M to N, right? And DSPS is related to the multi-excitonic characters. And what we actually can evaluate is this kind of matrix, Hamiltonian matrix. So we can actually evaluate this kind of electronic energies here and coupling between them. Okay, so this diagonal element is the energy of each microstate, and the octahedral element is the kind of excitonic coupling between local excitation and local excitation and charge transfer, and so on. And of course, the expression for this matrix element is already there. So we just reformulate the element within this density functional tight binding framework. So actually, this is the how to evaluate matrix element from Michael's paper. So we should evaluate kind of multi-center two-center integrals, so 2 index, 3 index, 4 index, and so on. The good thing is that the FTB has already there. So we implemented the kind of things, and this is the result. So we actually applied our methodology to the anthracene and tetracene dimers first. So in anthracene dimers, we have, for those dimers, we have kind of two configurations. One is herringbone. So it's kind of staggered like this one, and the other one is parallel. So we consider these two conformations for each structure. Then we use this kind of parameter set, and the reference is this the first principle calculation with this HeroCam software. So first one, we actually find nice molecular orbitals, the Kohn-Sham orbitals, so which is localized on each monomers, and these are the result for the excitation energies. So, well, for the local excitations, the charge transfer excitation, the result is quite good. It's comparable with this first principle calculation. So the error is within 0.0 few electron volt. However, the multi-excitonic character is not that good. Actually, in the FTB case, we have kind of overestimation of this multi-excitonic state, because this multi-excitonic state is actually related to the highly spin polarized state. Then it's actually beyond the conventional DFTB scheme, because DFTB is based on the kind of perturbative approach. So if you have large deviation of the ground state, then it actually gives more error. So we need more. Maybe we need some additional term, or we need better parameterization here. Then what about the couplings? So it's anthracene dimer case. We actually, where coupling is not that good, to be honest. So for the herringbone structure, we have quite reasonable and quite good coupling constant between these local excitations. However, between local excitation, charge transfer, or charge transfer multi-excitonic, the coupling constant is extremely small compared to the first principle calculation. And even worse, what is even worse is that for the parallel configuration, the local and coupling between the local excitation is actually still small, right? It's smaller than 1/2 of the original value here. So why? Because we actually think that in this parallel configuration, the molecules are more stacked, and in this coupling constant, we actually have some Coulomb part, several parts. One is Coulomb and exchange and kind of overlap. And in DFTB, we use the localized, the atomic orbital, the basis function. Then the overlap between these two, the overlap part is very small compared to the original value. So we think that this deviation comes from the kind of overlap. So we need some improvement. However, of course, the computational time is not comparable, right? But we can do the same thing for the tetracene, and actually we obtain the same trend. So I don't need to say that. And the final application is the anthracene crystals. So we need more larger system. So we want to actually investigate fluctuation of the external couplings, and actually we perform the ground state molecular dynamics with dense functional tight binding with this 300 Kelvin. Then actually we construct these 6 anthracene molecules in a unit cell like this way. Then here actually we have 4 parallel interactions and 3 actually herringbone interactions. And this is the result. So this one is our result, and this one is the result from this paper, which based on the TDDFT calculation. Where if you forget the number, if it exists, okay, then it's quite good, right? We have large fluctuation of this red one, and the red one is the herringbone interactions, and blue one is parallel, and small fluctuation of blue one, and we have this is the distribution of the couplings. Oh, it looks good, quite similar. And this is spectral density of this fluctuation, the Fourier transform of these fluctuations. It is reasonable. However, if you look at the value here, as you can imagine from the dimeric calculation, especially for this blue one case, the value is just half. So for the DFTB calculation, we have -0. The mean value is -0.018, and the TDFT value actually gives -0.035, so it's kind of twice of the value, right? So we still need some improvement of our methodologies. So actually that's it. So we actually developed 2.2 or 4.4 the DFTB SSR approach. So now we have long range correction and on-site orbital correction, so it is more generalized. However, with 2.2 is good. 2.2 is good. However, for 4 case, it's not that good. We need some improvement. So maybe one of the trend in this semi-empirical approach, for example, the dense functional tight binding case, we want to improve the accuracy. So we actually want to push the limit of the DFT, the result to the ab initio result based on the machine learning parameters. So maybe machine learning parameters can improve our data. So this is my group, and actually this work was basically done with Seung and Tae. So Tae is my student, and Seung got graduated, so he will move somewhere in a few months. And so these 2 people actually did some main work. And thank you for my students, and thank you for my funding source, and thank you for your attention.
One quick question, please. Okay.
Yes, self-conscious charge and long-range correction plus orbital correction. So maybe the third order correction is just one missing part in current approach. Yeah. Thank you.
Okay, let's thank our speaker again.
Okay, thank you.